Everyone, I am Mayank, and today I will be talking about a very critical and innovative topic, CerebroConvolve, which is focused on brain cancer detection using convolution techniques. So, with advancements in deep learning, especially convolution neural networks, we are now able to develop more accurate and efficient methods for detecting brain tumors. This technology not only speeds up diagnosis but also has the potential to save lives by providing early and precise detection. Let's dive into how these convolution techniques are transforming the field of medical imaging. So let's first understand the basics of brain tumor. As we see in the top left image, brain tumor can be categorized into two main types, benign tumors and malignant tumors. So as image shown on the left, benign tumors are non-cancerous. They tend to grow slowly and while they don't spread to other parts of the body. Whereas malignant tumors, these are cancerous and much more dangerous. They grow rapidly and aggressively. Now moving to this second image, we see a cross section of the brain. This highlights three of the most common types of brain tumors, which are meningioma, glioma, and pituitary tumor. Finally, as you see on the images on the right, these are MRI scans showing different types of brain tumors from glioblastoma to meningioma. This visual differences show why techniques like convolution can help radiologists identify and classify tumors with much more precision, reducing errors and speeding up the diagnosis process. So let's talk about the implications. Talking about the global impact, brain tumors have a high incidence and mortality rate worldwide. This highlights the critical importance of early diagnosis for improving patient outcomes. Catching these tumors early is crucial for effective treatment as delayed diagnosis can limit the success of available treatments and unfortunately lead to poorer survival rates. Talking about the limitations of traditional diagnostic methods such as BioSpy and CSF analysis have significant limitations. BioSpies, for example, are invasive procedures and carries risk like bleeding and inflammation. On the other hand, cerebrospinal fluid or CSF analysis, while non-invasive, can also lead to complications like infections. Preferred imaging modality, that's why where MRI comes into the picture. It is the preferred imaging modality for brain tumors. MRI provides high resolution images without the risk of invasive procedures, allowing for the more accurate and safer diagnosis. This imaging technique is especially important for early detection and planning treatments and forms the foundation of data that advances techniques like convolution neural networks. What's the need for automation? In traditional MRI analysis, radiologists manually examine images, which can lead to human errors and delays in diagnosis. With the increasing need for faster and more accurate diagnosis, there's a growing demand for automated tools. Computer assisted diagnosis CAD addresses this need by using technologies to assist radiologists in identifying abnormalities, speeding up the process, and reducing errors, ultimately improving patient outcomes. This diagram shows the full architecture used for brain tumor detection. We start with the two datasets, Figshare and Hardware Medical. These datasets contain MRI images of brain tumors, which form the foundation for our model. The data then goes through a pre-processing phase where the images are extracted, labeled, and prepared for training. Pre-processing is a crucial as it ensures the images are in the right format and labeled correctly for the model to learn from. Next, the data is split into training set and testing set. The training set is used to build the model, while the testing set evaluates how well the model performs on unseen data. Now we use two approaches. First, a 23-layer CNN model, which is ideal for large datasets. This deep architecture helps in learning intricate patterns in the MRI images to accurately detect and classify brain tumors. When working with smaller datasets, we use a combination of 23-layer CNN and VGG16 through transfer learning. VGG16 is a pre-trained model which helps in improving the performance on small datasets. Finally, we conduct a thorough performance analysis to assess the accuracy, precision, and effectiveness of these models in detecting brain tumors. This ensures the models are reliable and efficient in real-world applications. The Harvard medical dataset contains 152 MRI slices, whereas the Fixture dataset contains 3064 MRI slices. First, we split the data for both datasets into 70% training, 15% for validation, and 15% for testing, summing up to 100. So we ensure a balanced and reliable evaluation. During pre-processing, the MRI images were resized to 128 cross 128 pixels and converted from GIF to JPEG format. We also applied the data balancing techniques to handle any class imbalance using SMOT technique. Finally, our model achieved impressive results with accuracy of 97.8% on Fixture and whereas 100% on Harvard Medical. So talking about the data processing techniques as discussed earlier, Image conversion. The first step is converting the MRI images from GIF format to JPG format. This is important because JPG is more compatible with the model input requirements and reduces the complexity of image handling. Resizing. The MRI images are resized into standard resolution of 128 cross 128 pixels. This helps in ensuring the uniformity across the dataset, making it easier for the model to process the images efficiently. Channel replication. Since MRI images are often grayscale, we replicate the image across three channels to match the input size requirements for models like VG16, which typically expect RGB image. Shuffling. To avoid any bias, the data is shuffled. This ensures the training process doesn't follow any specific order of images and make the model more robust and less prone to overfitting. Finally, data augmentation. Finally, we apply various data augmentation techniques like rotation, flipping, and zooming to artificially expand the dataset. This helps in improving the model generalization by exposing it to more variations in the data. This slide explains the core component of a brain tumor detection model, the 23-layer convolution neural network architecture. Convolution layers are the building blocks of CNNs. Their main purpose is to automatically extract features from input images. These features can be simple patterns like edges and textures in the earlier layers and become more complex as we go deeper into the network, identifying shapes and objects. In each convolution layer, we have something called a kernel or a filter. This kernel slides over the input image and performs a mathematical operation called dot product. This helps in detecting important features in small regions of the image, which is crucial for tasks like detecting tumors in MRI scans. This process is repeated across multiple layers, allowing the model to progressively learn and recognize more sophisticated patterns, which is why CNNs are so effective for image classification tasks like this. So let's understand the architecture further. First, talking about input layer, we begin by feeding the MRI images into the input layer where they pass through several convolution blocks. Convolution blocks, the model has multiple convolution layers as shown in the blocks labeled block 3. Each block contains a combination of convolution operations, max pooling, and batch normalization. The convolution layers extract features from the images while max pooling reduces the dimensionality, and batch normalization helps to speed up training and make the model more stable. Average global pooling. After several convolution blocks, we apply global average pooling, which reduces the spatial dimensions and prepares the data for the dense layers. Dense layers. Next, the model uses fully connected dense layers. The dense layers further process the extracted features to classify images into one of the tumor types, pituitary, meningioma, or glioma. Dropout layer. To prevent overfitting, we use a dropout layer with a 20% rate, which randomly drops neurons during training and making the model more robust. Soft max layer. Finally, the output passes through a soft max layer, which assigns probabilities to each of the three classes, providing the final tumor classification. So let's see the mathematical part. This formula shown in the figure represents how a convolution operation works in a convolution neural network. CHW, this is the value of output feature map at position h comma w. Essentially, it's the result of applying convolution operation at specific point in the image. Ki comma j, this represents the kernel or filter, which is a matrix of size k cross k. The kernel is a small grid of weights that slides over the input image. These weights are learned during training process and they help in detecting feature like edges or textures. X h minus I comma w minus j. This represents the pixel values of the input image at each position h comma w. The kernel slides over the images, multiplies its values by the corresponding pixel values in that region, and then sums them up. The sliding process helps capture specific patterns from the input image and creates the feature map. In short, convolution is the process of applying filter across an image to produce a new filtered version of that image, which highlights the important features to learn from. So this is classic examples of how convolution works. So first there is an input matrix on the left. We have a 5 cross 5 matrix which represents the part of an image. Each number corresponds to pixel intensity at the specific location. For example, 3, 5 and 8 represent different brightness levels of the pixel. Kernel filter, in the middle we have a 3 cross 3 kernel. This kernel is essentially a small matrix that contains the weights. In this case it's 1 and 0, which will be applied to input matrix. The role of the kernel is to detect specific features in the input. For in this example, the kernel will slide on convolve over the input matrix, multiplying its values with the corresponding values in the input matrix. Convolution process, we move the kernel across the input matrix starting from the top left kernel. So let's take first example. Place the kernel over the top left corner of the input matrix, which includes the values 0, 0, 0, 0, 35 and 0, 7, 2. Now multiply each value by the corresponding kernel value that sums up to 0 into 0 plus 0 into 0 plus 0 into 0 plus 0 into 1 plus 3 into 1 plus 5 into 1 plus 0 into 0 plus 7 into 1 plus 2 into 0. The result is 8, which becomes the first value in the transformed feature map. Similarly, sliding the kernel, next the kernel moves one step to the right, stride of 1, and the same process is repeated. This time kernel overlaps with different parts of the input matrix and new value is calculated. Finally, we get a feature map. This feature maps looks like 8, 16, 13, 9, 13, 6, and 10, 14, 13 as shown. The feature map is a smaller, condensed representation of the input matrix, but it captures the important patterns. Activation functions are a crucial part of neural networks because they introduce non-linearity into the model, allowing it to learn more complex patterns. The ReLU or rectified linear unit is one of the most commonly used activation functions, and here's the mathematical part of it. The ReLU function outputs zeros if the input is less than zero and outputs the input value itself if it's greater than zero. Essentially, the formula is y equals to 0 if x less than 0 and y equals to x if x greater than equal to 0. This graph points to the left graph, illustrates this behavior. For any negative input, the function outputs 0, the flat light at the bottom, and for positive values, the function simply outputs the input value, the straight line going upwards. The diagram at the bottom sum up this in fun way. If you are below 0, there is a sad face. Relu shuts you off, but if you are positive, it shows a happy face and it lets you through. Relus are popular because it helps modern train faster by preventing vanishing gradients and keeps the computation simple compared to more complex functions like sigmoid or tanh. Max pooling layer. It is used to reduce the spatial dimension, height and width of the feature map while keeping the most important information. This helps decrease computational load and prevent overfitting by focusing on dominant features. So how it works, a pooling window typically 2 cross 2 slides over the feature map and for each region it selects the maximum value. This simplifies the data while preserving critical features. For example, with a 2 cross 2 window, it breaks the feature map into 2 cross 2 regions and selects the max value from each region to create a smaller, more refined feature map. So talking about the fully connected dense layers, after convolution and pooling layers, the output is still a multi-dimensional feature map. To connect it to fully connected layers, we first need to flatten the feature map into 1D vector. This process is handled by the flatten layer. Once flattened, the data passes through fully connected dense layers. These layers are crucial for learning from the feature extracted earlier. Each neuron in dense layer is connected to all neurons in the previous layer, allowing the model to interpret complex patterns. In this model, we use 4 dense layers. The number of units in each layer decreases as we move towards the output. We start with higher units like 5 and 2 and 256 and progressively reduces the size to fit into the number of output classes. The dense layers add a more sophisticated understanding into the features extracted, helping the model learn from which features are important for classification. Finally, the output layer softmax. Finally, we reach the output layer and which uses a softmax activation function. The softmax function converts the output into class probabilities, ensuring the sum of probabilities across all classes is 1. This is especially useful for multi-class classification as it helps the model determine the likelihood of each class. So this code defines the structure of sequential model using Keras. It includes 3 convolution blocks. First block uses a large 22 cross 22 kernel with batch normalization, radio activation, and max pooling. Second block, a medium 11 cross 11 kernel with the same components, whereas the third block, a smaller 7 cross 7 kernel following the same process, refining features at each step. Each block extracts progressively more complex features from the input image. This slide highlights the key results achieved by our model. Accuracy on the fixture dataset. The model achieved an impressive 97.8 accuracy on fixture dataset when broken down by tumor types. Meningioma with 96.7% accuracy, glioma 97.2% accuracy, whereas pituitary tumor 99.5% accuracy. This indicates the model's strong performance in classifying different types of brain tumors. Performance metrics. The model demonstrated high performance with an average precision of 96.5%, a recall of 96.4%, and an F1 score of 96.4%, showcasing its ability to detect brain tumors effectively across different cases. The ROC curve for the fixture dataset had an AUC or area under curve of 0.989, which indicates excellent model performance in distinguishing between different tumor types. Talking about the overfitting challenge, on the hardware dataset, the training and validation accuracy were about 95%, but the testing accuracy was low, suggesting overfitting due to smaller dataset size. To address this, we integrated the VGG916 model with its 23-layer CNN, which helped overcome the overfitting issue and improve the model generalization. This bar chart illustrates the performance of a model across three different tumor classes. Meningioma tumor class, the model achieved an accuracy of around 96.7% with slightly lower precision and recall in the range 93 to 94%. This indicates strong classification performance, though there is room for improvement in precision and recall. Glioma tumor class, for gliomas, the accuracy, precision, and recall are close to 97%, indicating consistent and high quality performance across all metrics. This suggests the model is very reliable in detecting glioma tumors. For pituitary tumor class, the model performed best, achieving nearly 100% accuracy and strong precision and recall values, both above 95%. This shows model is highly effective at identifying pituitary tumors with minimal errors. Overall, the model shows high accuracy across all tumor classes, with best results for pituitary tumors, followed by gliomas and meningiomas. So here is the two visualizations of these results. Talking about confusion matrix, the confusion matrix shows how well our model predicted different tumor types, comparing the true labels with the predicted labels. For meningioma, the model correctly identified 140 cases as meningioma but made 9 errors, misclassifying them as glioma. Glioma, the model correctly classified 270 cases as glioma but made 8 errors, classifying them as meningioma. For pituitary tumor, the model almost perfectly classified all pituitary tumors, just made 2 errors out of 182 cases. This confusion matrix highlights the model performed very well. Talking about ROC curve, the receiver operating characteristic curve. The ROC curve evaluates the model performance by plotting the true positive rate against the false positive rate at various thresholds. The AUC area under curve is 0.989, which is very close to 1, indicating excellent performance in distinguishing between different tumor classes. A higher AUC means the model has strong ability to differentiate between the true positive and false positive cases, which is crucial for accurate diagnosis. So thank you for all your time and attention. I hope this presentation gave you valuable insights into how convolution techniques can help improve brain tumor detection. Thank you.